Good morning, everybody in chemistry. I hope that you are having a great day and we are looking forward to a short week. Hopefully you're going to get out and enjoy this nice weather that we're supposed to be having. Well, we're going to turn to our notes here. We're going to have our third podcast. We talked about the combined gas law in class. So go to the bottom of that page and we're going to talk about volume and moles in Avogadro's law. Now, when we first talk about this law, it's probably not going to seem like a really big deal to you. But once Avogadro was able to prove this law, it really opened up a whole lot of studying in the gaseous phase. And it was really attributed to him that more theories and laws were able to have some direction and start realizing that their research is really having some validity. So he was able to say that the volume of a gas is directly proportional to the number of moles. Temperature and pressure remains constant. Now keep in mind, temperature and pressure, that's not anything. Just remember that if you're in Hastings, Minnesota, and in our classroom, the temperature and pressure are going to remain constant. So you can continue to do your studies. So if you take a look at the bottom of page 455, and if you don't have your book, it's fine. Just make a note and look at it later. All the figure is showing you is that if they add the number of moles, you can see where n equals 1, and then n equals 2, and n equals 3, that the volume is also increasing by the same amount. So it's just a good picture for you guys to take a look at. And all this is saying then in Avogadro's law is that these two things are proportional. So you will just simply see that the volume is proportional to n. And V is for volume, which we've been using all along, and n is equal to the number of moles. So if we take this one step further and take a look at how this can be applied, Avogadro's hypothesis continued to say that if I have equal volume of gases at the same temperature and pressure, because we know that gases are greatly affected by both of these, and contain the same number of particles. So here's our STP again. Remember, at STP, standard temperature and pressure, 760 millimeters of mercury, or 273 Kelvin. That 1 mole, here's that number we haven't talked about for a long time, 6.02 times 10 to the 23rd of any gas occupies 22.4 liters. Now that may not seem really exciting to you, but what that did is if you take a look at my example that I had down here, I have 1 mole of helium, meaning I have 6.02 times 10 to the 23rd particles of helium. I have 1 mole of xenon, meaning 6.02 times 10 to the 23rd particles of xenon at STP. In both cases, look, they both take up 22.4 liters of space. And look at their difference in mass. This was a huge breakthrough, you guys. And so what we're saying is that we don't care about the identity. It doesn't matter what it is. 1 mole of any gas, that is something that you really need to get to understand. Any gas is 22.4 liters. And here's our formula, just showing you that it is a direct proportion. And if you want to look at it, V1 over the number of moles, that should recognize to you that that is going to be a direct proportion. And what they simply did here then in your book is they cross-multiplied and gave you this formula. V1 times N2, V2 times N1. All right, so now we have an example for you on this. And again, we need to make sure that it doesn't say this is at STP. So because it's not at STP, we are not using 22.4 liters per mole. We're just going to use our equation. So we have our variables, V1, we have N1, we have V2, and we have N2. So we have a 12.2 liter sample, and we recognize that liter is going to be volume, and a 0.5 mole of oxygen at 1 atmosphere of pressure. The temperature is 25. If all of this oxygen is converted to ozone, what will be the volume of the ozone formed? All right, so let's take a look at what we already know. We already know that we have 12.2 liters, which is going to be our volume. We know that we have 0.5 is going to be our mole. We know our pressure and we know our temperature, and it looks like that is going to be remaining constant. And that's all we know. Well, we do know that oxygen is being converted to ozone. So I should be able to write a balanced equation. So I have my oxygen, it's all being converted to ozone, which is O3. And I need to go back and balance this, so my common factor between 2 and 3 will be 6. So I have 2 moles of this to 3 moles of that. Well, now we're going back to partial stoichiometry, and hopefully some of you are going woohoo right now. And we understand that we are given 0.5 moles of oxygen gas. So if I have 0.5 moles of that, I should be able to go and find what my moles of my unknown is. So I'm just going to use, remember those keywords, unknown over known. We haven't said those in a while. So my unknown is 2 moles of O3, and my known is going to be 3 moles of O2. Do the calculation, and I get 0.33, yep, 2 sig figs right here. Just want to make sure that that's right. 0.33 moles of O3. So as I take a look at that, now I can go ahead and I can continue to fill in here. I have 0.33 moles of this. Then I can figure out what is the volume of my ozone that's going to be formed. So just simple plug and chug like we talked about, just plug in the numbers and go ahead and do the algebra. So we know that we have V1 times N2 equals volume 2 times the number of moles in the beginning situation. So my volume here is going to be 12.2, sorry about that, and N2 is going to be 0.33, and my new volume is going to be my X, that's what I'm trying to determine, and N1 is going to be 0.50 moles. Go ahead and solve and do your algebra magic there, and my volume is going to be 8, and I can't read my writing, wow. So 8 something is going to be my volume here. And so it's trying to take a look at that. If you look, you can see my volume went from 12.2 liters down to 8 liters. That means my moles should also decrease, and they do. So we have again verified Avogadro's hypothesis. All right, so you guys can go ahead and try this practice problem, and if you have the correct answer, you should find the number of moles is to be 0.67 moles. And then you guys can go ahead and make sure that you work on these review questions also. But just chosen 3 of the ones that are stated there on page 457. All right, this is just going to be a short little lesson on Avogadro's law. Again, we just need to really make sure that, impress upon you that you understand that 1 mole of any gas, did I say that strong enough, is equal to 22.4 liters if I am at STP. All right, have an awesome day, you guys.